Welcome back to the second fundamental theorem of calculus discussion. We ended on that last section and just barely getting into the net change theorem. So the net change theorem says, if we know that by the second fundamental theorem of calculus or the fundamental theorem of calculus part one, again depending on who is writing the textbook, when we take the integral, we've got the antiderivative. We plug in the b and so on, right? And if we take the integral on a derivative of a function, then we just end up with the original function, right? They undo each other, right? So this is referred to as the net change of f. So the integral of a derivative is just your original function. So I think this is oftentimes best illustrated when you're discussing position velocity, which we know as the derivative of position, velocity, acceleration, which is the derivative. Acceleration is the derivative of velocity. So if we take the integral of the velocity, right, that'll take us back to the position, and then it's evaluated as a b at b minus a. So if this is time t, right, this is giving you the displacement of a particle, right? If you're if you've got this particle that's moving left and right, let's look at a graph here for just a second. So this is the integral of the velocity, again, is your position. Here's the function graphed, the velocity, and let's say we're going from time 1 second to, I don't know, 5 seconds, whatever. Okay, so this velocity, remember, velocity has magnitude. So this particle, which is moving right or left, right now it's positive. It's all positive right here until the third second. So from the first second, um, wherever it's at, this thing is moving to the right till the third second, and then the velocity it stops, right? The velocity is 0 there. And then it backtracks. The velocity then gets negative down here, right? So it backtracks for a second, and then at the fourth second it stops again, and then it goes to the right, back to the right. Right? So it went this way, then it went back that way, and then it goes that way. The total displacement is subtracting those two, right? Maybe it started out at 2 feet away from the origin and ended at 10 feet away. So the total displacement, there's 8 feet difference. But the total distance traveled, that's a different story. Total distance traveled, it's more than 10 because, maybe it went this way, I don't know, 7 feet, then it went back 2 feet, so there's 9 feet plus those two more plus whatever more. Maybe the total distance ended up being 13 or 15 feet or whatever it is, right? Total distance. And so if you're taking the integral, you have to take the integral on the absolute value. In other words, you have to consider the integral of this area right here, area 1, plus area 2. Remember, this is negative. When you run the integral, that's negative. So let's say this total distance was 7. Uh, this total distance was maybe 4, but it's going to spit out -4. So you got to run the absolute value on that. And then this total distance is 2. So it'd be 7 plus that integral plus 2. So in this case, it ends up being 13 feet is the total distance traveled, even though maybe it was only 8 feet or whatever in terms of displacement. Okay. So let's do a problem with that. What's the displacement of the particle on the time interval from 1 to 5 for this function t cubed minus t squared, 10t squared plus 29t minus 20. So the total displacement, we're just going to run the integral, right? That's total. Even though it went back and forth and back, whatever it did, where did it end up minus where did it start? So we just run the integral on that. So you end up with 32 thirds feet to the right as your total displacement. So, and sure enough, it did. It went to the right and then it went to the left. Okay. Now, total distance, total distance, the first thing you want to do is you want to think about, well, for this function, where's your zeros? It looks like it hits here. When does the velocity, when does the velocity zero, when does it stop and potentially move in the other direction? So you get your zero, so you factor it, t minus 1, t minus 4, t minus 5. So it hits at 1, 4, and 5. And the total distance would be this area, plus this area. Again, this will be negative, so you got to run the absolute value there. Okay, so we're going to go the integral from 1 to 4 of the velocity. And then we're going to go from 4 to 5 dt, but we're going to slap the absolute value on that. Okay, we just got to run through the calculus with that. And there's your calculus for it. You know, run through 1 to 4. In this case, in this display, they just put a negative in front of it instead of just going plus an absolute value. You could do either one of those as long as you change the sign so that that thing ends up being positive. You know, you get 45 force plus the 7/12, right? So you get 71.6 is the total distance traveled on that one. Thanks so much for listening. That's your net change theorem. See you guys next time.